Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 43. Now in the previous lecture, we were obtaining the relationship between the various processes that happen as matter interacts with light. For example, we were discussing about the processes of absorption, spontaneous emission and stimulated emission. And using the ideas of black body radiation and local thermal equilibrium, we obtained an expression for U. We call this equation U, where U, is the energy density, the spectral energy density per bandwidth, okay, right? Which has units of joules per meter cube second. This is obtained from black body radiation, right? And under the assumption of local thermal equilibrium. I think I used the phrase thermal equilibrium in the previous lecture. I want to add one more point as local thermal equilibrium. That is to make it clear that we're not talking about any global context. The system of consideration, for example, the particular like matter that is absorbing the radiation or emitting the radiation, that alone is in equilibrium with its surroundings. Okay, right? So I want to use the phrase local thermal equilibrium. In shorthand, it's LTE. This phrase LTE or this abbreviation LTE is going to be often encountered, in astrophysics, astronomy, and occasionally also in astrochemistry. Okay, so get to know this phrase, right? The local thermal equilibrium. We shall in fact elaborate upon this more in this lecture. And also note that your U is equated to A21 divided by N1 by N2 times B12 minus B21, where my A21 corresponds to the spontaneous emission coefficient, the Einstein coefficient for spontaneous emission, right? Recall from the previous lecture how we obtained this A21. Corresponding to spontaneous emission, we had the term, right? dN by dt, the dN2 by dt for the spontaneous emission is equal to minus N2 times A21, right? For absorption, we took a positive sign, so therefore, for the emission, we had to take a negative sign, right? Recall? So please take a look at the previous lecture note for the exact enunciation of these two terms. So this corresponds to spontaneous emission, the 21, and B21 terms corresponds to the stimulated emission, right? Wherein, a photon hits an electron in an excited state, and therefore the electron falls down. And B12, of course, is the absorption coefficient, all right? And we also had this derivation under the assumption that the net rate of electron transfer under local thermal equilibrium is going to be 0, right? So with that brief introduction-ish, discussion, we shall now proceed further. Okay, so what did I keep saying so far in this lecture? That we were working under the assumption of local thermal equilibrium, LTE, right? This is something I frequently told you. Now, is there, I want to ask you folks, besides today's lecture and the lecture before it, that is lecture 42, was there any other occasion when I actually used this phrase thermal equilibrium in this course? Do you remember the conditions when, the situation or conditions when I was discussing thermal equilibrium? In what lecture? The exact number even I don't know, but while on the discussion of what topic? Well, as it turns out, if you remember, while discussing the similarities, between the interstellar medium, the similarities and differences between the interstellar medium and Earth, we were constantly using this phrase thermal equilibrium, right? Whenever thermal equilibrium holds good, we have a condition called as a Boltzmann distribution. Remember? Under LTE, this is a T or a tau, okay, right? Under LTE, the Boltzmann distribution for the population of molecules holds good. So please make a note of this. All right. Now, what is the Boltzmann distribution itself? What is the Boltzmann distribution? One form of it. Okay, right? One form of it says that if one corresponds to a lower level or a ground state, and 2 corresponds to an excited state, the population of species, in this case the electrons in these 2 levels, is given by this term right here. Is given by G2 by G1. Don't worry about what G is yet. I haven't introduced this term yet. Times e to the power minus delta E by kVt. Right? Now, how did we get this expression? We did not derive it, okay, right? We are just using this expression. So, note, we use this expression from statistical mechanics. And recall that we are not deriving it. So there is a whole branch in physics and chemistry called as statistical mechanics. And from this, this expression can be derived. There are various versions of the same expression, but we need not go to the details of them. Just take this equation for granted. Okay. Now, you may ask me a natural question. Of course, I take this equation for granted. Let's call this expression B in honor of Boltzmann. Okay. And you may ask me, okay, I take this equation for granted, but so what now? I don't understand it, right? So the next step would be to actually try to make sense of the equation. So the LHS, that is like the N2 by N1, we already discussed. We are using the same notation as used for our discussion on Einstein coefficients. Okay. So that is N2 and N1. On the RHS, well, E is the irrational number, and delta E is what? Delta E is the energy difference between N2 and N1. And notice that delta E here is equal to h nu, right? Because it takes 1 photon to go from N2 to N1. So we might as well, substitute this delta E with h nu. All right. So what is Kb? Kb is the Boltzmann constant. We have been looking at this repeatedly in this course. And T is the temperature. The only unknown terms, in this equation are G2 and G1. So what are G1 in equation B? Well, the technical term used for G2 and G1 are what are called as degeneracies. Okay, right? It's called as a degeneracy. And what is the meaning of this phrase? New jargon is fine, but what does it mean? Well, it refers to number of states having the same energy. We're not going to derive this expression, but I will briefly tell you the intuition, as to how exactly, these 2 terms come up. Okay, right? Number of states having the same energy or in the ground state, right, which is labeled by 1, and the excited state. You may be wondering, well, it's already a ground state. So what do you mean by number of states in a state having the same energy, right? That may be a very valid question, but I'll answer that very soon. Okay. So to understand degeneracy, okay, now consider a hydrogen atom. Okay. I'm sure everyone must have studied about hydrogen atom in your 11th and 12th standard, right? Now, what are all the orbitals that a hydrogen atom has? What all are the orbitals that a hydrogen atom have? Any answer? What I'll do is, I need both expression U and B. So I will just write it in a box here. So to understand degeneracy, right? So to understand, okay, to understand this thing, degeneracy, right? I'm going to use this box to explain it to you. So you all heard about hydrogen atoms, right? Now, so the hydrogen atom has what all orbitals as part of the hydrogen atom? The hydrogen atom has s orbitals, yes, and then p orbital, d orbital, and f, and so on, right? It just so happens that we are only concerned with when we consider populating the electron in a hydrogen atom, we shall be populating in the s orbital, which is the least energy orbital, the 1s orbital, right? This is from 11th and 12th standard, not even college, okay, right? That's why I'm just stating these as facts. Now that you have all these states here, if you consider the p state, that is like the p orbitals, do you understand that the p state is threefold degenerate? Or in other words, right, the p orbital, right, has conventionally px, py, and pz, all of which have the same energy. Unless and until, of course, like you put the molecule in the magnetic field, okay, right? So a priori, without like putting the molecular atom in a magnetic field, px, py, pz have the same energy. So therefore, the degeneracy for this state p, right, is said to be 3. So the degeneracy, what I'll do is, I will now that we understand what question we are talking about, I'll erase the top part of this board. I'll call this itself as page 4, okay, right? And I'll just delete the question. So the degeneracy of a p orbital in hydrogen atom, right, in the absence of a magnetic field, okay, please understand this. Is going to be 3. Similarly, now that I've explained to you what a p orbital is, right? I mean the degeneracy using the idea of p orbitals. What is going to be the degeneracy of your d orbitals? There are going to be 5 d orbitals having the same energy, right, in the absence of a magnetic field. So therefore, the degeneracy, I'm just going to call this g, using the same notation I'm using in this expression b here, okay, right? So similarly, g for a d orbital is going to be 5, right? And g for an f orbital is going to be what? 7, correct. And the g for an s orbital is 1, right? Because there is only one, corresponding to any principal quantum number, there is only one L associated with that. That is like L equal to 0 associated with that. So the degeneracy of the s orbital is going to be 1. So without even deriving this equation, right, we kind of have an idea about the degenerate states. In other words, it refers to the number of states in either the excited state or the ground state which have the same energy. And I illustrated that to you using the idea of the s, p, d, f, etc. orbitals in the hydrogen atom. Are we clear? Okay. So, in fact, also, please make note. Don't think that, just because the hydrogen atom, I mean, I know that some of you might have this question. Just because it's a hydrogen atom, do not assume that it only has one electron. So therefore, the p, d, f orbitals, etc. are not present. No, the p, d, f orbitals are always present. Orbitals are mathematical functions, okay, right? They can always be associated with any atom, okay? So they'll always be present. And so when I refer to a p orbital, it is always going to be triply degenerate in the absence of a magnetic field. Are we good, right? Okay. So now we've understood, how these terms G2 and G1 arise, and note that G2, G1 are integers, okay? G2 and G1, they're always integers, and they're always greater than or equal to 1. Can the degeneracy be 0? No, okay, right? The degeneracy can never be 0. the minimum value of degeneracy is going to be 1. Okay, so now that we've understood this expression right here, you know, that the Boltzmann distribution, right, wherein your ratio of the number of molecules or the number of electrons in this case, right, is given by N2 by N1, which is the LHS, that is given by G2 by G1, where G2 and G1 are the degeneracies, where I just told you what degeneracy is using the idea of orbitals, times e to the power minus h nu over kBt. So this is the local thermal equilibrium, LTE conditions, wherein Boltzmann distribution holds good. Okay, right? All right. Now, having explained equation B now, I'll delete this part again. Now what I'm going to do is, I'm going to, you know, substitute this value. I have something like N2 by N1, right? So I can invert it. That is like I can take the reciprocal and get N1 by N2 also. That is just going to be the reciprocal of this thing, right, on the RHS. And I'm going to use it in this expression U right here. Okay, right? For a long time, this part of the board was unattended to, but now it's time to, you know, use expression B, right? Expression B to get N1 by N2 in equation U. All right. Once I do this, I'll go to the other part of the board, which is page 5 now, and I shall be getting my U to be equal to A21 divided by G1 by G2, right? G1 by G2 times e to the power minus h nu by kBt, correct? E to the power minus h nu by kBt times B12 minus B21. Okay, so we get this expression by using the Boltzmann distribution here in equation U. We get a modified expression for U. Okay, right? Now note just one point. I think I made a small mistake in this equation, right? This N2 by N1 should be G2 by G1 times plus h nu. Okay, right? So because, you know, if this minus were to be coming here, right? If this minus were to be coming here, here we know it is like N1 by N2. All right, yeah. So it's what you call a typo, right? When you type. So on the board I made a typo. So this should not be e to the power minus h nu. Please notice this right away. Okay. So this should be e to the power h nu here. So that when we take the reciprocal, right, this term here becomes e to the power minus h nu by kBt. Are we good? Right? So G2 and G2 by G1 times e to the power plus h nu by kBt is expression B. Earlier on, you know, I had by mistake a minus sign here. That needs to be corrected. And once that is corrected, that is, this is e to the power plus h nu by kBt, then this naturally follows because it's N1 by N2 over there. All right. So please correct it. So this is going to be A21 divided by this denominator. Are we clear? Are we also clear about the mistake I made and the correction I suggested? Earlier, you know, there was a negative sign here before h nu. That had to be a positive sign, right? So that when I take the reciprocal, this will also be G1 by G2, and this e to the power will be like going to the denominator, and 1 by e to the power something is e to the power minus something, which is showing up here. All set, right? Okay. So having corrected this mistake, and now we have this term right here. This u can also be further modified as, I'll just, you know, divide by B21. Okay, I'll divide by B21 throughout, and this is going to be, of course, assuming that, you know, it is not 0. So this is going to be A21 divided by B21, right? I'll tell you the purpose behind this very soon. Okay, right? So this is A21 divided by B21, divided by G1 by G2, G1 by G2 into this B12 by B21, right? Times e to the power minus h nu over kBt, correct? Minus 1. All right. Now notice that, you know, notice that this is not this thing, this whole thing minus 1, okay, right? This minus 1 is separate. Okay. I'll in fact put it even better. I'll write it such that times e to the power minus h nu divided by kBt minus 1. Okay, so points to note, this minus 1 is not part of the exponent, and these three terms are multiplied and minus 1 is separate. Okay, to be absolutely clear, I'll add one more bracket here to indicate that this minus 1 is not part of the common multiplied term here. This minus 1 is separate, and it is not as part of the exponent. Are we fine? So are we fine with this expression completely? Okay, so what do we have here? We have an expression, let's just call it this is expression u, which is modified by using LTE, that is like using local thermal equilibrium, right? So and after including the Boltzmann distribution, I'm just going to call this equation BU. Okay, right? Now if we compare equation u and BU, now because equation no, we need not compare equation u and BU, so we obtained BU. Are we clear? I hope I was clear in my enunciation, right? I didn't make this mistake, but after that it was all smooth. We have an expression, and subsequently we divided the numerator and denominator by B21 term to get it in this specific form. And the key thing to note is that this minus 1 is outside this complete bracket. Okay, that's it. So now I'll delete this part. Now recall that this u, this term u, where did it come from? It came from black body radiation, correct? Because Einstein assumed that whenever there was spontaneous absorption or stimulated emission, in both the cases, it was not just about the number of electrons, but it's also about how much of radiation is emitted, right? That is why Einstein included this term u, from black body radiation, correct? Okay, so recall that from black body radiation, for which we've been using this abbreviation BB in this course, right? From black body radiation, u is actually given by, if I'm correct, okay, u is given by 8 pi h nu cube, right? 8 pi h nu cube divided by c cube times 1 over e to the power h nu over kBt minus 1, right? This is from black body radiation. In fact, we even discussed in a tutorial about its dimensions and units and all this, right? So I hope you remember this. Okay, now let me just call this as like expression BB from black body radiation. We also have one more expression, which is BU, right? Which is obtained from the local thermal equilibrium assumption based on the connections between the various Einstein coefficients. Now if we compare these two equations, right, now this u is the same as this, that is the LHS of equation BB, right, and the LHS of equation BU are the same, which means that the RHS also have to be the same, right? The RHS also have to be the same, and the forms are somewhat similar. The forms of like this term right here, right? It is of the form 1 over e to the power h nu by kBt minus 1, and here also there is something like some term divided by e to the power minus h nu by kBt minus 1, but there are some prefactors. How do we compare the two equations? Now notice this. Okay, now if you actually notice this, if your A21 divided by B21 is equal to, right, this term right here, 8 pi h nu cube by c cube, right? If this is exactly equal to this, right, then this whole thing, this G1 by G2 times B12 by B21 and G1 by G2 times B12 by B21 is equal to 1. What are we doing? We're just like looking at equation, the expression for u from the black body radiation and comparing with whatever we derived for the Einstein coefficients, the connection between Einstein coefficients as part of light interaction with matter under LTE conditions, that is under local thermal equilibrium conditions, and we obtained two somewhat similar looking expressions, and based on that by comparing the numerator and denominator, right? If, we have this A21 by B21 is equal to this term right here, and this whole multiplicative factor to be unity, then we understand that because the LHS are the same, right? Then the RHS will also be the same. Are we clear? See, eventually the LHSs are the same. U here and also U. It's the same U that we are talking about. Okay, right? U, right? It's the same U. Having said that, if the LHSs are the same, then if these are valid, right? If these conditions between the A21 and B21 with like the 8 by H, G cube by C cube, etc., if they are valid, then the RHSs will also be the same. Are we good? Right? And so what have we done? What have we done through this process? What have we done is that by comparing the expression for U that you obtain using the LT approximation, right, with the U obtained using the black body radiation model, we have connected the Einstein coefficients. Okay, right? These are all called as the Einstein coefficients, A21, B21, etc. Okay, right? So we understand that, I'll write it down here. By comparing, okay, right, overall, by comparing, right, BB, equation BB with equation BU, right, we could connect the Einstein coefficients. We can connect the Einstein coefficients A21, B21 and B12, right? Because from this expression, if one of them were to be known, we can calculate another, right? And therefore, from this expression, because like one of them, the degeneracies could be computed, and we could find out yet another Einstein coefficient also. Okay, so all the three Einstein coefficients could be connected, right? That's the objective. But what are we going to achieve by connecting the Einstein coefficients, and what is the connection with astrochemistry? In fact, we could connect the terms A21, B21 and B12, right? And especially, right, this specific term B21, which is the coefficient for spontaneous emission, this could also be obtained from quantum mechanics, independent of this derivation. Okay, right? So knowing this, we can calculate the other coefficients. And what is the connection with astrochemistry? Knowing all this, right, all these terms could be connected with the intensity of a spectral line. Right? So all of these three Einstein terms could actually be connected with the intensity of a spectral line. Okay. How exactly, I haven't told you. Yet so far, right? We shall see how this is done and how is the connection made between the Einstein coefficients and intensity of a spectral line, which is of course very important for the detection of molecules in space. Okay, right? And overall, we can get all the other terms also based on the connections made and the rates of transitions, that is the rate at which an electron gets excited to a higher level or comes back to a lower level, a ground state to excited state or an excited state to ground state in the context of astrochemical electron transitions, which is what happens, right, when light interacts with matter be it in space or on Earth. Okay, so therefore overall the connection is very important for us to understand the rates of transitions of electrons from ground state to excited state, which is extremely vital to detect molecules in space. On that note, I end this lecture here, and we shall continue in the next class. Thank you so much.